welcome back. So we are discussing our third chapter in this course, which is measurement of resistance, and in this video we will talk about low resistance measurement. We will start talking about low resistance measurement, and in particular we will talk about 4 terminal resistance. Quite amazing, isn't it? A resistance which has 4 terminals. Generally we know resistance has 2 terminals. Okay, so let's understand that. So we are talking about low resistance measurement. And so let's consider of a situation, okay, and so I particularly request you to listen to this particular topic very carefully, because this is one topic which I myself had confusion or doubt for many years. Okay, so this is really very and for young people, I mean new students, this is very confusing, and there is no shame if you feel that it's confusing. Okay, so please listen to this very carefully. It's going to be interesting. Okay, it's going to be very interesting. So let's think of very small resistance, maybe around 1 ohm. Okay, so this is a piece of resistance around 1 ohm or maybe even less. Okay, so maybe less than 1 ohm, so very small resistance, and I want to measure this resistance, okay, in a lab. And how do I do that? So this is small resistance and I will use voltmeter ammeters. Okay, now so I have to connect an ammeter and a voltmeter. Okay, now say I connect an ammeter to measure the current that flows through this resistance. So I connect the ammeter in series. Okay, and then I want to measure the voltage across it, so I connect a voltmeter, and you can connect it to a source, otherwise no current will flow. Okay, so this way what I can do, I can look at the reading of this voltmeter and the reading of this ammeter, and then estimate the resistance R, so call it Rx, unknown, as the voltmeter reading, by ammeter reading. Okay, so this is normal procedure, but I am saying that don't do this. Okay, don't use this circuit. Why? Because if you recall, in our previous video we talked about that for low resistances, do not connect the we should not connect the ammeter directly across this or directly besides this resistance, because then this ammeter has also some internal resistance, and that may be low. Ammeter resistance is low normally, that's what the ammeter resistance should be, it should be low, but this resistance is also low. So therefore these two resistances are comparable. Okay, so if this is 1 ohm, maybe this is also 1 ohm or several ohms, and therefore if I connect the voltmeter across these two in series, I am actually measuring more voltage, much more voltage than the voltage across this resistance Rx. So this is not a good circuit, and therefore we have seen there is a better circuit. So don't use this circuit, this is a bad circuit. Okay, don't use it, rather use this circuit where you can connect a voltmeter directly across this resistance Rx, Okay, so this is again the same small resistance, maybe less than 1 ohm, and then you connect the ammeter, and then you connect the power supply. Okay, so definitely voltmeter resistance is much higher. I mean, voltmeter resistance ideally is infinite, practically maybe several kilo ohms, and then of course this circuit is therefore better because the current through the ammeter, most of it goes through this resistance and a very little amount goes through this voltmeter. Okay, so this circuit is better. Okay, so this circuit is better, and then once again you can measure Rx as the voltmeter reading, whatever the voltmeter shows divided by the ammeter reading. So this is actually a recapitulation of what we have done in the previous video. Okay, so this is a better circuit, and we need RV, voltmeter resistance. Okay, now I guess it's clear when I write RV, it means voltmeter resistance should be very high. Okay, infinite, theoretically that's what we want, but it's never infinite. But if you recall from your high school physics, we can measure voltage also using potentiometers. So we can measure voltage using potentiometers as well. Okay, and the nice thing about potentiometer is that we'll talk about potentiometers in more detail later, but from your high school physics you can recall that potentiometers also can measure voltage, but the nice thing is that at the null condition of the potentiometer, no current goes through the potentiometer. So if I have a potentiometer instead of voltmeter, okay, that will be even better. So let me, instead of having a voltmeter, let me use a potentiometer. Okay, so right now I am drawing it as a black box. What's there inside potentiometer, how it's connected, that we are not going to discuss. So potentiometer, right now you think of a potentiometer. Okay, so for now you can think of potentiometer as a voltmeter with infinite resistance. It's equivalent to an ideal voltmeter with infinite resistance. Okay, so for now it's enough that I mean, we'll talk about potentiometer in more detail later, but to focus our attention on this topic, low resistance measurement, you think of potentiometer as an ideal voltmeter. So there exists something like a ideal voltmeter with infinite resistance. Okay, so for now let's think in that way. So the circuit we should use to measure a low resistance is this. This is the low resistance. We should have the potentiometer or voltmeter with infinite resistance. Okay, so here directly across it, so this is where we will measure the voltage. This can be a potentiometer or a very good voltmeter, and then we'll have the ammeter, and here we will have the power supply. So this is the circuit. Now we know that you might have seen that we have resistance boxes. You might have seen resistance boxes in lab. So those are like wooden boxes with terminals. So we have a wooden box with leads or terminals, and inside it we have the resistance inside the box, and then we can connect wires to this terminals. So this is a resistance box. Okay, and this resistance Rx, which is a small resistance, low resistance, can also come in a box with two terminals. Okay, so therefore in this experiment we can connect the wires to these terminals. Okay, now if we do so, let's see what will actually happen. So note that these terminals also have some resistance. Everything has some resistance. The wires have some resistance. These terminals have some resistance, and this resistance of this terminal will also depend on how, say, tightly you connect this wire, how much pressure you applied. So the resistance will depend on, on a lot of things. Okay, so if I draw this resistance simply like this, so this is a low resistance, small resistance, low resistance with two terminals which I am drawing as two knobs, two circles. So these are these two leads, and wires are connected here. Okay, now this lead will also have some resistance. Okay, now let's consider this circuit once again. So we have the voltmeter connected here, an ideal voltmeter or a potentiometer. Okay, it's connected here. So the terminals of the potentiometer or voltmeter is connected to this lead and this lead. Then the ammeter terminals are also connected to this lead, and the supply is here. Now this will have some resistance. This lead will have some resistance. Okay. Now, so this is very important. So this leads will have some resistance. For ease of understanding, so let's think that the lead resistance will cause some small resistance added in all these three branches which are connected to it. So this will cause some small resistance being equivalent to some small resistance here, and some small resistance here, and some small resistance here. Okay, so this is like if I have a lead where 2-3 terminals are connected. Okay, so these are wires, and this is equivalent of saying that I have some small resistance, some small resistance, and some small resistance being contributed in all these three branches. Okay, because of this lead. Similarly, here also we'll have some small resistance, some small resistance, and some small resistance here. Okay, now do you see a problem? The problem is that this part of the small resistance contributed by the connection is getting added to this low resistance. Although this is small, so this is small, this is definitely small, this is small, but this is also small. So therefore these are comparable. Maybe this is just maybe I don't know, half a ohm. Also maybe this is quarter ohm, but this is also a small resistance. Maybe this is just 1 ohm or less. So these two are coming in series with this resistance. So we have a significant amount of error. If this is like say half a ohm, if this is like half a ohm, and this small resistance is like 1 ohm, then actually between these two terminals I have total of 2 ohm resistance. So this is a large error. But it wouldn't have been a problem actually if this 0.5 ohm and this 0.5 ohm was constant. Okay, so let me note that it would not be a huge problem if the contact resistances were constant, but it is not constant. So for example, when I measure this resistance using this voltmeter ammeter method, so I apply some voltage source, some current is flowing through this ammeter, I record the ammeter reading and the voltmeter reading, and I get some voltmeter reading. Next day I come and do the same experiment, but the next day I do not make these terminals, that means these leads, as tight as it was on the previous day. Okay, so the first day say I made this terminal very tight, and the next day I was doing it differently and I didn't make it so tight, it was loose. So then maybe this resistance says, this contact resistances which will come in picture in series with this resistance, that will be different. Okay, say that then for day 1, when this current I was say 1 ampere, okay, so say I have a resistance rheostat, so I was varying this, and so therefore this current was varying. So in day 1 I had this stable voltage versus current, voltage or current versus voltage maybe, so current and voltage, and then for 1 ampere current I got some reading, maybe the reading was 1 volt. For 2 ampere I got the reading 2 volt, and so on in day 1. And in day 2, when I was doing the same experiment and same current was flowing 1 ampere, then 2 ampere, the voltage reading which I was getting here was not same. It was coming say 1.5 volt, 2.9 volt, and so on. Why? Because maybe the next day I didn't make these terminals as tight as it was on the first day. So these small resistances which are coming in picture, they were different. So therefore, and you see this voltmeter, this is an ideal voltmeter, and the voltage that it's measuring is the voltage across this small resistance plus this series contact resistances. So therefore, if these contact resistances are varying, then for same amount of current, the voltmeter reading will be different. Okay, so here for first day, my estimated value of Rx was like, so V by I, it was like 1 ohm, but on the second day, my estimate is like up almost like 1.5 ohm. So that's the problem with this setup. Okay, so I hope the problem with this setup is clear. The problem is due to the fact that the contacts these contacts have some resistances. They are small. Okay, they are small, and generally we do not bother about them. But when this resistance which you are measuring itself is small, then anything small compared to this resistance is significantly large. This is small, this is also small, so they are comparable. Okay, and more crucial problem is that these contact resistances are not constant. So if I do this experiment 3 days, 4 days, every day I will get different reading. So this way I cannot say what is the value of this resistance. Now I will give you the solution to this problem. Okay, so the solution to this problem is as follows. So solution to the above problem. Okay, solution is, if this is the small resistance, okay, then attach 4 leads to it. Two on either side. Okay, so you have 4 leads, 2 on this side, 2 on this side. So maybe if I draw it in a box, so I can draw it like this. So if this is a wooden box, a resistance box, okay, so where this is the small resistance inside, from this, here you connect one terminal, here you connect another terminal, another lead, okay, and this is soldered inside. So this is a permanent joint. So this joint is not going to change or alter anyway. Similarly, connect another terminal here. Again, this is soldered. Another terminal here. Again, this is soldered. Okay, so this way I have 4 terminals. Okay, let me call them as like P1, P2, C1, C2. These are just some names I'm giving right now. Do not bother about why P, C, anything. Okay, so this is what is there inside the box. Okay, so here let me similarly call this as, so 2 of them as P1, P2, C1, C2. Okay, so one P on one side, another P on another side, one C on one side, another C on another side. Now what I will do, I will connect the source of current. Okay, so what I want to measure this resistance using Ohm's law, using a voltmeter and an ammeter. So I need a power source, so which I connect across this. Okay, so now current can flow through this resistance, and I have to measure this current. So I connect the ammeter in series with this resistance, and I have to measure the voltage across this voltmeter. So I need a voltmeter or a potentiometer, which is a near perfect voltmeter. It's with infinite resistance you can think of. That I will connect here across these 2 terminals. Okay, okay. So now what happens? Now it can think that all these terminals, they will contribute some small resistance here and some small resistance here. Similarly, this will contribute some small resistance here and some small resistance here. Similarly, some small resistance will come here and here. Here also some small resistance here and here. Okay. 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 Now the what is this voltmeter is measuring? This voltmeter is measuring the voltage across itself, and we know that the current through the voltmeter should be small. Why it should be small? Because this resistance is much higher than this resistance, so most of the current goes through this resistance. So if this current is I, then most of it will go through this, and very little amount will go through this. So the voltage drop across this lead you can ignore, because this current is small, and also compared to this resistance is much higher. So RV is much higher than, okay. So let me give these resistances some names, like let me call this R1, R2, R3, R4, R5, R6, R7, R8. Okay, now RV is much higher than R1, R2, R3 and R4. Therefore, the voltage drop across the voltmeter is almost same as the voltage drop across this resistance. Okay, so voltage drop across voltmeter, which is same as voltmeter reading, okay, is almost same as the voltage drop across the unknown resistance, call it Rx. This is the small unknown resistance. Okay, you can also use a potentiometer. Then this current at null condition will be 0. So this current, okay, this small current, call it IV, through this branch, okay, then this current, then IV is 0 at null, okay. Therefore this voltmeter, or this potentiometer actually, is measuring the right voltage, okay. Thus the potentiometer, or let me write it, thus the voltage measurement is perfect. Thus the voltage measurement is not disturbed. It's okay, it's perfect, almost disturbed. It's not disturbed by contact resistance. Okay, now even if I do this same experiment for 2-3 days, when I have a different amount of pressure and tightness, so that this R2, R4, their values, here R1, R3, their values change when I do this experiment in different days, even then this voltage reading is okay. You can think of a potentiometer or a high internal resistance of voltmeters, so that these resistances are so small, and also if this current is 0 for potentiometer, so therefore the voltage measurement is perfect, and it's no way disturbed by the value of this contact resistances. Okay, so R1, R2, R3 and R4 doesn't create any problem. Why? Because, so observe that firstly this, if we are using a voltmeter, okay, and IV is equal to 0 if we are using potentiometer. Okay, so you may revisit this video after you study potentiometer. Okay, so therefore the voltage reading is not disturbed by these contact resistances. Anyway, these contact resistances are very small compared to RV. Now the next question I'll ask this question to you: does or do R5, R6, R7 and R8 create any problem? These R5, R6, R7 and R8. So do they create any problem? Think of a bit. The answer is no. Why? Because you can think all these resistances as a part of this, supply circuit. Part of the, maybe it's, you can think of this as the part of this rheostat, or part of this internal resistance of this voltage source, so, or the ammeter. So all these resistances, they do not, I can think of they are part of this supply circuit, and this doesn't create any problem. Okay, because what we measure the value of this voltage for a particular amount of current through this ammeter. So we measure this voltage for, say, 1 ampere current through this ammeter, and that will give this resistance Rx. Okay, now whatever resistance I have in this circuit, they do not create any problem. You can think that this is, they all together are series resistance, which is a part of this rheostat, which you are changing to vary this current. So this resistances, they do not come into picture at all. So no. So they do not create any problem. So they are not in the picture at all. Okay. So these contact resistances do not matter. And these two contact resistances which affect this voltage reading, but the effect is small because these resistances are much smaller than the RV. Okay. So think of this very carefully and think of considering the fact that how your result might get changed if you repeat this experiment and the previous experiment many a times when your contact resistance is changing. Okay, how much error you may get. Okay, so think in this term, in this way. In our next video, we will take some concrete examples, some concrete numeric examples to make this more prominent, more clear. Thank you.